All right, so on the back here, average rate of change we said was slope over an interval. I'm going to add a little bit of vocabulary to that. It is slope of a secant line. And where you may have heard that word before, slope of a secant line, is back in geometry when you do the whole circles unit. You know how you had like a circle and then there was a line that went through it like this and it hit at 2 points and it was called a secant line? That's where that comes from. So it is slope of a secant line. It's over an interval, so it's going to hit the graph at 2 points. But that's just your basic regular old algebra 1 slope. It's rise over run, or change in y over change in x. This is delta y over delta x. That just means change in, or m for slope. So it's just your regular old algebra 1 slope. And I'm going to draw a picture over here for us to have a visual of this. So I'm just going to draw a graph doing something. And I'm going to pick a point on the graph starting here. So I'm going to call that x. And so its y value is going to be f of x. So if I input x, my output is f of x. And then I'm going to come down here over an interval, and I'm going to go a distance of h units. And so this point will be x plus h. So if I start at h, and I'm walking a distance of, if I start at x and I'm walking a distance of h, then this point would be x plus h. And so on the graph, that output value would be f of x plus h. I realize that's like, hey, Miss Cole, you're putting every letter of the alphabet in here, but are y'all still with me? We have x, f of x, and then we have x plus h, f of x plus h, just input and output. So if we were going to do this slope from this graph, and this is called a difference quotient, and they use that vocabulary on the AP exam too. They'll be like, write a difference quotient for this. It is just your regular old slope. We're going to subtract the y values. So it'll be this one minus this one, f of x plus h minus f of x, over, and then we're going to subtract the x values. Now, if you do this one minus this one, the x's are going to cancel. You'll have x plus h minus x, so it will just be h. And so that is your difference quotient. We're subtracting the y values and then dividing by subtracting the x values. And that's what difference quotient means. Difference means you're subtracting. Quotient means it's a fraction. So that is your average rate of change. Instantaneous rate of change, instead of slope of a secant line, this is slope of a tangent line. And again, where you would have seen that before is back in geometry, again in the circle unit, when you had a circle and the graph just kind of came by and kissed the circle at that one point, that is a tangent line. And so that should make sense that this is instantaneous. It's just touching at that one point. So this is secant line, this is tangent line. And so what we call this is a derivative. And our notation for a derivative, there's several different ways you can write it. You'll see it as f prime of x, or y prime, or dy dx. It means derivative of y with respect to x, but it's differential y over differential x. It means the exact same thing that it meant here. This is all slope, okay? So if you see any of those notations, that's what derivative means. That's the notation that means derivative. So using this difference quotient that we have, instead of over an interval between these 2 points, we want it to just be at x. So I'm going to draw in the secant line. The secant line would look like that. And what I'm going to do is slide this point this way a little bit. So if I move it over, then that distance is shortening. And if I keep moving it, that distance is going to get shorter and shorter and shorter until I end up with a tangent line to the graph at that point. So if I'm sliding this point this way, does that feel like a limit? It should, because that's what this is going to be. I'm making this distance h smaller and smaller and smaller and smaller. I'm sliding this point here until they are going to be on top of each other. So it is this. We just want the limit as h goes to 0. We want that distance of h to be nothing. So it is limit as h goes to 0 of our difference quotient. So I just recopied this and stuck a limit in front of it. It is limit as h goes to 0. F of x plus h minus f of x over h. Do you need to know that formula? Yes. But for heaven's sake, it's a slope, so I think you'll be okay. Everybody is every year. And then just slap a limit in front of it to make it calculus. This is algebra. This is calculus. This is average rate of change, instantaneous rate of change. So we're going to practice using this formula on some problems. Letter A, here's our function. Find the average rate of change over the interval 3, 7. Well, average rate of change just means the slope between those points. So we need a point for 3, and we need a point for 7, and then we're going to do the slope between them. So how can we get these y values? What are we going to do to get those? Yeah, good. Plug them in. All right. If we plug in 3, we're going to get 15 plus 1. That'll be 16. If we plug in 7, we're going to get 35 plus 1, which would be 36. And then we're going to do the slope. So 36 minus 16 over 7 minus 3. That's going to be 20 over 4, which would be 5. That should not be a surprise. Why does it make sense that that was 5? If you look at this equation, why does 5 make complete sense as an answer? Yeah, good. The slope is 5. The slope of this line is 5, and a rate of change means a slope, so slope's going to be 5. No, I love when you guys answer. Don't ever feel shy about answering. Or you can also answer to me privately, but I like when we're having a conversation. All right, that keeps me engaged, honestly, when you guys are talking to me, so I don't feel like I'm talking to myself because I can't see you. Yeah, slope is 5. So honestly, if you get asked for an average rate of change and your graph is linear, it's just going to be the slope. So you can just put that as your answer. All right, finding the derivative, that is this thing. All right, it's going to be a whole big bunch of algebra, so hold on. And if you haven't been writing anything down, you're probably going to want to write this down because it's a lot of steps and you need to practice them. So we're going to start with limit as h goes to 0. And then the first step is you're going to plug x plus h into the function. So if I plug x plus h into this function, that's going to give me 5 x plus h, and then the plus 1 is just there. So that's this first part. And then it says minus f of x. So I'm going to subtract the whole function. So I'm going to subtract this. So I'm just going to copy that right here. And then that is all over h. So you write your limit, h goes to 0, plug x plus h into the function, subtract the function, and then put it all over h. All right, so here comes all the algebra. Distribute the 5 through here. That'll be 5x plus 5h, and then plus 1. Distribute the negative into here. And then it's all still over h. And then at this point, if you have done your job correctly, stuff should cancel out. The 5x's are going to cancel. And then the plus 1 and minus 1 is going to cancel. So that's all gone. You're left with 5h over h. And so the h's also cancel. And all you're left with is 5. And so our derivative is 5. I want you to start getting used to this notation. You can pick any one of these 3 that you want. I'm going to use f prime of x. but our derivative is 5. That's what we got. Again, that should make sense because this is a line and the slope is always 5. For a line, it's going to be up 5 over 1, up 5 over 1, up 5 over 1 infinitely. So the slope is just always going to be 5. So if you want the instantaneous rate of change at 3, f prime of 3, the derivative at 3, that would be 5. If you want the instantaneous rate of change at 7, that would be 5. And if you want the instantaneous rate of change at 14 billion, that would be 5. If it's a line, it's just always going to be the slope. You're probably like, hey, Ms. Cole, what if it's not a line? Well, I'm glad you asked, because we're going to do this example here. I can't get this to print right, and I apologize. This should be 2 square root of x. I need to go back and mess with this document and try to fix that. But every year I'm just like, yeah, it's really easy to scratch that out and fix it, so I've never done it. But this should be 2 square root of x. That is not a line. A square root graph does something like this. It's a curve, so you're not going to have a nice even slope the whole way through. So first one, average rate of change on the interval 1 to 9. That just means slope. And you should be happy I picked 1 and 9 because those are perfect squares, so that's going to make our life easy here. So if we plug in 1, square root of 1 is 1, times 2 is 2. If you plug in 9, square root of 9 is 3, times 2 is 6. And so when we slope those, that will be 6 minus 2 over 9 minus 1, which will be 4/8 or 1/2. So average rate of change over that interval would be 1/2. Find the derivative. Okay, that's this formula. So again, if you haven't been writing anything down, maybe at least do this, because this is what's going to be a lot of steps. All right, I'm going to try to write small here, make it all fit. I tried to get this to all fit on one page. Right. Limit as h goes to 0, and then you're going to plug x plus h into the function. So I'm going to put x plus h right here. So it's going to be 2 square root x plus h. And then minus the function. So that would be minus 2 square root of x, and then it is all over h. If you're like, that looks like a mess, you're right. In order to cancel out roots, we have to multiply by the conjugate. So for this one, that would be 2 square root of x plus h plus 2 square root of x. It's this exact same statement, but instead of subtraction, we're putting addition. And again, if you feel overwhelmed by that, that is totally okay. That does look overwhelming. Just remember, in this next step, a lot of stuff is going to cancel out. So most of this is going to go away. So if you were feeling nervous, don't worry. This next step is going to be better. So when we multiply these, 2 times 2 is 4. And then these roots are going to cancel and just give you x plus h. So you end up with 4 times x plus h, which will be 4x plus 4h. And then when we multiply these, -2 times 2 would be -4. And then these roots cancel and it'll just be x. So minus 4x. For the denominator, you want to do nothing to this. Just copy this over. I realize that's like annoying to copy that over, but it goes in the annoying but not difficult category. Just don't do a copy error because those are a bummer. All right, so I just copied all that over. Now we're looking for stuff to go away. So these 4x's are going to cancel. And again, if you do your job properly with these derivative questions, stuff is going to cancel out. Those are gone. And then what else is going to cancel? Now that this is all I'm left with, what can I cancel out next? Yeah, good. The h's are gone. And so my numerator is just 4. This is going to be my derivative here, f prime of x. Or you could write y prime, or you could write dy dx, whatever is your preference there. My numerator is just 4. And in the denominator, I'm plugging in 0 for h. Again, if you don't write this limit, you might forget to plug in that 0, so just be careful. So if that's 0, I've got 2 square root of x plus 2 square root of x. So together that would be 4 square root of x. And you can leave this like this, but those 4's actually also cancel. So you can write it as 1 over square root of x. And so that is our derivative. And if you're like, hey, Ms. Cole, this derivative came out to a number. This one has a variable in it. That is a good compare and contrast thing. This one had a constant slope. It was just always 5 no matter what number you wanted to plug in. Here, this is going to change depending on what x is. So if we want to do the instantaneous rate of change at 16, f prime of 16, if you plug that in, you're going to get 1/4. But say you wanted to do the instantaneous rate of change somewhere else, like say you wanted to do f prime of 9. I'm picking perfect squares to make these answers come out nice. Say you wanted the instantaneous rate of change at 9, then what would you get? Yeah, good, 1/3. So see, this instantaneous rate of change is not going to always be the same. It's going to depend on whatever x is. This one was always the same. And again, that's because that was a line. All right, so we're going to try one more. A car is traveling according to this function. If the d for distance and the t for time bothers you, you can rewrite it as f of x. There's nothing wrong with that. That is totally fine. The car is traveling for 2 hours. Time is in hours, and d of t is in miles. So we've got miles per hour. Ooh, the speed limit is 55 miles per hour. So find the average rate of change on the interval 0 to 2. Average just means a slope. We want a slope from 0 to 2. So if we plug in 0 to this, 0 for t, we're going to get 0. If we plug in 2, let's see, 2 squared is 4, times negative 25 would be negative 100. And if we're plugging in 2, that would make this 200. So negative 100 plus 200 would be 100. And then doing the slope will give me 50 miles per hour. So what that means is over the time interval 0 to 2, the car averaged 50 miles per hour. But does that mean that it didn't speed at some point? Well, I'm not sure. This is just an average. The car averaged 50 miles per hour over that interval. If you want to know how fast the car was going at a particular moment, then you need a derivative. So that's what we're going to do for part B. So again, and I'm not going to slide the paper up and down and make you seasick, but it's this same formula, all right? Same as we did for these two. So limit as h goes to 0. And again, this is the one, if you haven't written down anything else, you want to write down this part. All right, we're going to plug x plus h into this function. Look out, because there are 2 places where there's a variable in this function, and you have to put x plus h in for both of them. All right, so I plugged x plus h into both of these. And then minus the whole function. So I'm just going to put this whole thing right here. And I'm going to use x's because I've got x here with the x plus h. And then that is all over h. Okay, so the next step is not going to be super fun because we're going to have to multiply all this out. But just remember, after that, almost everything should cancel out. So there's like one step that's kind of annoying, and then most of the stuff should go away. So looking at this, x plus h squared, I'm just going to write this off to the side. That means x plus h times x plus h. So if we multiply that out, we're going to get x squared. Outsides are xh, insides are xh, so that would be 2xh. And then h times h is h squared. So that is this part, and we need to distribute a negative 25 to each part of that. So I'm going to distribute a negative 25 into that. All right, that was the hardest part. We got that taken care of. Next, I'm going to distribute this 100 into here. So plus 100x plus 100h. We got to make sure our algebra skills are good here to get through this. And then we're going to distribute the negative into here. So plus 25x squared minus 100x. All of this is over h. Phew, we did it. Okay, now we're looking for stuff that goes away. So what do you guys see that is going to cancel? It should hopefully be a lot. We want a lot of things to go away. Good, 100x's are gone. And the 25x squared is gone. Is there anything else? That might be it. Oh yes, and then the last thing is h. Good. In order to cancel out the h, we have to factor it out. So I'm going to factor h out of what's left. So that would leave us with negative 50x minus 25h plus 100. And then the h's cancel. I get a lot of people that want to cancel the h without writing this factoring step. If you can do that in your head, that's fine with me. I do caution against that though, because at the end you have to plug in 0 for h, and it's hard to see this if you don't write it out. It's only one more step. My suggestion is just go ahead and write it out. All right, so if we plug in 0 for h, this is gone, and we are left with negative 50x plus 100. So that is our derivative. Negative 50x plus 100. So if we're asked for the instantaneous rate of change at 1 hour, that means f prime of 1. We're going to plug 1 into our derivative. So let's see. If we plug in 1, negative 50 plus 100 would be 50 miles per hour. That means at time 1, the car would be going 50 miles per hour. Oh, wait, and I got something in the chat. The negative 25, oh, the negative 25x squared's canceled out. We had a negative 25x squared and a positive 25x squared, so those were gone. And same with the plus 100x and minus 100x. Oh, we plugged in 0 for h. And that's, so Ethan brings up a good point. This is what I was saying. People will try to skip this step and jump straight to the answer. No, you're fine. I'm glad you brought that up because that illustrates my point that I was trying to make exactly. If you try to skip this step and not factor out the h and jump right to the answer, you miss that. You have to plug in 0 for h. And so this is what you're left with. Okay. So this is asking for instantaneous rate of change at 1, but we could plug in other numbers. Like what if we wanted to plug in like 1.5? Like what if you wanted to know the instantaneous rate of change at 1.5? Well, let me plug that in. And I get 25. So that means at time 1.5 hours, the car was going 25 miles per hour. But the question is, did the car ever speed? So let's go back. What was the speed limit? Speed limit was 55. We need to know if this instantaneous rate of change was ever greater than 55. So I'm going to take this, negative 50x plus 100, and set it bigger than 55, and we're going to solve. If we get an answer, then yes, the car was speeding during that time. If we get something that doesn't make any sense, then it'll be no. So subtracting over the 100 will give us negative 45. And then we're going to divide by negative 50. Does anybody remember what we have to do when we divide by a negative? If we're doing an inequality, if we divide by a negative, what do we have to do? Yeah, good. Flip the sign. So x less than, all right, negatives cancel. 45 divided by 50 is 0.9. So we got an answer. If your times are smaller than 0.9 hours, the car was speeding. Now I actually have to add to that this needs to stay bigger than 0 because we don't have negative times. But yeah, the car was I say the car was speeding as though there wasn't a driver and it was going all by itself. We won't blame it on anyone. The car was speeding from 0 hours to 0.9 hours. And we can show that if we want to plug in a number to the derivative that's between 0 and 0.9, like say we plug in a half, like let me plug in a half an hour. That would give us half of 50 would be 25, negative 25 plus 100. The car was going 75 miles an hour then. So what happened was the car was going super quick for this first part, but then it slowed down enough later that its average rate of change ended up being below the speed limit. But the car did speed for that first section of time.